The illusion of stillness. The night sky presents an illusion of stillness. When you look upward, the patterns of light seem fixed, quiet, and unchanging. Yet, every point of light is undergoing a profound, steady process of change. The stars are not static objects. They are participating in a very long, very slow cycle of formation, existence, and gradual fading. This cycle spans billions of years, a scale of time so vast that a single human lifetime is but a fleeting moment. Tonight, we will trace the factual sequence of a star's life. We will follow the slow gathering of dust, the steady warmth of a star in its prime, and the eventual quiet return of its material to the galaxy. The story begins in the deep, cold spaces between existing star systems. Throughout the galaxy, there are vast, drifting clouds of gas and dust. These regions are known as molecular clouds, or stellar nurseries. These molecular clouds are unimaginably large. They sometimes span hundreds of light years across. They are characterized by extreme cold, with temperatures hovering just above absolute zero. In this profound chill, the particles of gas, mostly hydrogen and a small amount of helium, move very slowly. There is no sound, no sudden movement. There is only the slow drift of atoms in the expansive dark. The patient pull of gravity. For a very long time, these clouds remain in a state of quiet equilibrium. The internal pressure of the cold gas pushes outward. This is perfectly balanced by the faint, persistent pull of the cloud's own gravity pulling inward. However, this balance is sometimes disturbed. A slow-moving density wave passing through the spiral arms of the galaxy can shift the gas. The gentle push of stellar winds from a distant older star can also cause the gas and dust in a particular region to compress slightly. When this happens, the balance shifts. Gravity, the most patient force in the universe, begins to take over. As a pocket of the cloud becomes slightly denser than its surroundings, its gravitational pull naturally increases. This increasing gravity causes more nearby gas to be drawn inward. As the material gathers, it falls toward the center of the newly forming mass. This process is not rapid. It takes hundreds of thousands of years for the gas to slowly accumulate. As the material falls inward, the particles begin to rub against one another. This friction generates a very small amount of heat. Over a vast stretch of time, the center of this collapsing cloud begins to warm. It is now a protostar. At this stage, it does not emit visible light. It is wrapped in a thick, insulating blanket of its own dust. It glows only faintly in infrared wavelengths, hidden from typical view. Deep within the core of the protostar, the temperature continues to rise steadily. Gravity relentlessly packs the hydrogen atoms closer and closer together. The pressure builds, steadily and inevitably. The protostar continues to gather mass from its surrounding envelope, settling into a spherical shape. Eventually, the temperature at the very center of the core reaches approximately 15 million degrees Celsius. At this specific threshold, a fundamental shift occurs. The hydrogen nuclei, which typically repel each other, are moving fast enough and are packed tightly enough that they are forced together. They fuse, creating helium. This process is known as nuclear fusion. When hydrogen fuses into helium, a small amount of mass is converted directly into energy. The long equilibrium. This energy radiates outward from the core. For the first time, the outward pressure generated by the heat of fusion at the inward pull of gravity. The collapse finally stops. The star stabilizes. It has entered the main sequence, which is the longest and most stable period of its entire life. For a star similar in mass to our Sun, this period lasts for about 10 billion years. During this vast stretch of time, the star changes very little. It simply sits in the vacuum of space, steadily converting hydrogen into helium in its core. It radiates light and heat out into the darkness. The star is a perfect sphere of balanced forces. Gravity tries to pull the star inward, while the energy from the core pushes outward. They are matched perfectly. The star hums with a steady, consistent energy. It provides a reliable source of light, a calm anchor for any planets that may have formed in orbit around it. As the billions of years pass, the core of the star slowly accumulates helium. This is the natural byproduct of the fusion process. The hydrogen in the very center eventually begins to run low. Without the steady energy of hydrogen fusion to support it, the core begins to slowly compress under the weight of the star's outer layers. As the core compresses, it heats up even more. This additional heat radiates outward, warming the layers of hydrogen gas that immediately surround the core. This introduces a new phase of fusion within the aging star. The hydrogen in this shell surrounding the core begins to fuse, generating a new source of energy. This new outward pressure is stronger than before. It pushes against the outer layers of the star, causing them to gradually expand. As the star's outer layers stretch further away from the heat of the core, they naturally begin to cool down. The light they emit shifts in frequency. The star changes from a bright yellow or white to a deep, warm red. It has become a red giant. This expansion is a very slow process. If you were observing the star over millions of years, you would simply see it growing steadily larger and redder. It is a quiet swelling in the dark expanse of space. A slow expansion. For a star like the Sun, its outer layers will eventually reach out far enough to envelop its closest planets. The red giant phase is a period of slow, inevitable change as the star adjusts to its shifting internal chemistry. Deep inside the red giant, the core continues to compress. It eventually becomes hot enough to fuse the accumulated helium into carbon and oxygen. This provides a temporary new source of stability, but it does not last nearly as long as the main sequence. Eventually, the helium in the core also exhausted. For an average-sized star, the core will never become hot enough to fuse carbon or oxygen. The end of its active life is slowly approaching. The outward pressure begins to falter. Without the outward pressure of fusion to support them, the very outer layers of the red giant begin to drift away. The gravitational hold of the core on these distant, expanded layers is very weak. Slowly, the star sheds its outer envelope of gas into the surrounding space. This gently expanding shell of gas is called a planetary nebula. It forms a beautiful, faint sphere or ring of illuminated material, slowly drifting outward into the interstellar medium. Left behind in the center of the nebula is the star's exposed core. It is no longer fusing elements. It is entirely composed of densely packed carbon and oxygen. This quiet, glowing remnant is called a white dwarf. A white dwarf is incredibly dense. A teaspoon of its material would weigh tons on Earth, but it is entirely inactive. It is simply a hot, glowing sphere, radiating its remaining thermal energy into the cold vacuum of space. Over billions and billions of years, the white dwarf will slowly cool. Its light will change from white to yellow to a dull red. Eventually, it will fade completely. It will become a black dwarf, a cold, dark sphere drifting silently through the galaxy. The planetary nebula that once surrounded it will have long since dispersed. The gas and dust will mix with the interstellar medium, ready to eventually become part of a new molecular cloud. The path of the massive stars. This gentle fading as the fate of stars with a mass similar to the Sun. However, stars that are much more massive follow a different, though equally natural, path. A massive star progresses through its life stages much more rapidly. Its immense gravity creates extreme pressure and heat in its core. This causes it to burn through its hydrogen fuel very quickly. A massive star might consume its initial fuel in a mere few million years. When the hydrogen is gone, the massive star swells into a red supergiant. Because of its greater mass, its core can achieve the temperatures necessary to fuse heavier and heavier elements. It fuses carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. The production of iron is a definitive turning point. Fusing iron does not release energy, it consumes it. Suddenly, the outward pressure, that has supported the star for its entire life ceases entirely. The core, composed of iron, finds itself bearing the crushing weight of the entire star. The balance of forces is broken. In a fraction of a second, the core collapses in on itself. The outer layers of the star follow, rushing inward at an immense speed. When this infalling material hits the dense, collapsed core, it rebounds. This sends a shockwave outward, expelling the star's outer layers into space. This event is a supernova. A supernova is a profound redistribution of matter. It scatters the heavy elements forged within the star across vast distances. These elements, the carbon, oxygen, iron, and others, will eventually drift and cool. They will mix with clouds of hydrogen to seed the next generation of stars and planets. A return to the dark. What remains after a supernova depends on the original mass of the star. If the core is of a certain mass, the collapse stops when the protons and electrons are crushed together to form neutrons. This creates a neutron star. It is a sphere roughly the size of a city, but containing the mass of a star. It sits quietly in the dark, spinning and slowly cooling. If the original star was even more massive, the collapse cannot be stopped by any physical force. The matter continues to fall inward until it is concentrated into a single point of infinite density. This is a black hole. It is a region of space where gravity is so strong that nothing, not even light, can escape it. A black hole represents a quiet, absolute endpoint. It is an invisible presence settling into the fabric of space. Whether a star fades quietly as a white dwarf or collapses into a black hole, the outcome is a return to stillness. The energy has been spent, the elements have been forged, and the material has been returned to the galaxy. The scattered gas and dust will drift for eons. It will slowly cool in the deep silence of space. Eventually, inevitably, gravity will begin its patient work once again. A new cloud will gather, a new core will warm, and the long, quiet cycle of stellar life will begin anew. The universe continues its slow, steady respiration. Like and subscribe for more incredible facts about our universe.